Imagine you are lying still in the dark right now, and somewhere out there, billions of light years away, there is a place where space itself stops making sense. Where light, the fastest thing in the universe, simply cannot escape. Where time slows down so completely that, from the outside, a single second could stretch into 1,000 years. That place exists. It is real. And tonight, we are going to drift toward it together, slowly, gently, the way you might float on still water on a warm evening, carried by a current you cannot see but somehow trust completely. There is something about black holes that has always called to the human mind, not because they are terrifying, though they can sound that way at first, but because they sit right at the edge of everything we know. They are the universe's way of showing us that the rules we take for granted, the rules that govern every single moment of your ordinary day, are not the whole story. They are just the story we can see. And just beyond the horizon of what we can see, there is something stranger and more beautiful than almost anything else in existence. Before we go any further, if you are enjoying this kind of quiet journey through the universe, the kind where you can close your eyes and let the words carry you somewhere vast and peaceful, consider hitting the like button and subscribing so you never miss a night like this one. It takes just a moment, and it means these conversations can keep going, drifting through the cosmos together, one slow evening at a time. Now, let us talk about black holes. Most people, when they hear the words black hole, picture something like a drain, a cosmic sink at the bottom of the universe, pulling everything toward it, hungry and violent and dark. And while that image is not entirely wrong, it is missing something important. It is missing the stillness, because black holes, for all their impossible power, are in many ways the quietest things in the universe. They do not roar. They do not flash or explode or announce themselves. They simply exist, with a kind of absolute, unmoving patience that has no parallel anywhere in nature. Think about the most patient thing you have ever known. A mountain, maybe. The way a mountain just sits there across thousands of years, through every storm and every season, utterly indifferent to the passage of time. A black hole is like that, but turned up so far beyond any scale we have words for that the comparison almost breaks. A black hole does not measure patience in thousands of years. Some of them will outlast the universe itself. They will still be there, silent and perfect, long after the last star has gone cold. So tonight, as you lie there in the quiet, I want you to let go of the idea that black holes are something to be afraid of. They are not coming for you. The nearest one is so incomprehensibly far away that the number of miles between you and it would take longer to read aloud than you have been. Alive, you are safe, you are still, and from this stillness, we can look out at them with nothing but wonder. Let us start at the beginning. Not the beginning of black holes, we will get there, but the beginning of understanding them. Because black holes were not discovered with a telescope. They were discovered with a pencil. In 1915, a man named Albert Einstein sat down and rewrote the rules of gravity. Not because the old rules were broken. Isaac Newton's version of gravity had worked beautifully for over 200 years, but because Einstein suspected the old rules were incomplete. He suspected that gravity was not really a force at all, in the way we usually think of forces. He suspected that gravity was something far stranger. He suspected it was the shape of space itself. Here is an analogy that might help. Imagine you are holding a large bedsheet stretched out flat, and you place a heavy bowling ball in the center of it. The sheet curves downward under the weight. Now, if you roll a marble across that sheet, the marble will not travel in a straight line. It will curve toward the bowling ball, following the slope of the sheet. That curving path is what we experience as gravity. The bowling ball is not reaching out and grabbing the marble. It is simply bending the surface, and the marble follows the bend. Einstein's great insight was that space and time, bundled together into what physicists call spacetime, works something like that sheet. Massive. Objects bend spacetime around them, and everything else, including light, follows the curves that massive objects create. This was the theory of general relativity, and it was so precise, so elegant, and so strange that it took the scientific world years to fully accept it. It predicted things that seemed impossible. It predicted that light could be bent by gravity. It predicted that time could slow down near a massive object. And buried inside its equations, it predicted something that Einstein himself found deeply uncomfortable, something he hoped was not real. It predicted black holes. The mathematics of general relativity contains a solution, a set of conditions under which the equations describe a point in space where gravity becomes so intense that not even light can escape, where spacetime curves so sharply that the curve becomes a closed loop, where there is no path that leads out in any direction at any speed, a region of absolute no return. Einstein looked at this solution and did not like it. It seemed too extreme, too clean. He wrote papers arguing that it could not exist in nature, that some other force or process would always prevent things from going that far. He was wrong, and the universe, as it turns out, makes black holes with remarkable regularity. But how? How does something like that actually form? The most common way begins with a star. Not a small star like our sun, though our sun is not small by any ordinary measure, but a star many times more. Massive. A giant, burning with a light so intense that if you could somehow stand on a planet close to it, the warmth on your face would be enough to reduce you to nothing in an instant. These stars burn bright and fast, consuming their fuel at a furious rate. And when that fuel runs out, when the nuclear fires at the core finally exhaust the last of the hydrogen and helium they have been fusing for millions of years, something remarkable happens. The fire goes out, and when the fire goes out, there is nothing left to push back against gravity. All that time, while the star was burning, the outward pressure of the nuclear reactions at its core was perfectly balanced against the inward pull of its own enormous gravity. It was a balance point, a kind of perpetual standoff, sustained over millions of years. But the moment the fuel runs out, the balance collapses. Gravity wins. And it wins so completely, so suddenly, so catastrophically, that the entire mass of the star, sometimes 10 times, 20 times, 30 times the mass of our sun, collapses inward in less than a second. Less than a second. Think about that. Millions of years of burning, and then the entire collapse happens faster than you can blink. The outer layers of the star explode outward in one of the most energetic events in the known universe, a supernova, a burst of light so bright it can briefly outshine an entire galaxy of hundreds of billions of stars. But the core, the dense, crushed heart of the dead star, keeps collapsing. It collapses past the density of ordinary matter, past the density of an atomic nucleus, down and down into a point of infinite density that physicists call a singularity. And around that singularity, like a perfectly drawn circle in the fabric of space, appears the thing we have come here to talk about tonight, the event horizon. The event horizon is not a surface you could see or touch. It has no wall, no membrane, no material edge. It is simply a boundary in due space, a threshold, a line drawn by the mathematics of gravity that separates two regions, one from which escape is possible and one from which it is not. Cross that line in the wrong direction, and the universe as you know it simply ends. Not with a bang or a crash, just a boundary, invisible as a thought, beyond which there is no coming back. The name itself is beautiful when you understand it. An event horizon works like the ordinary horizon you see on a clear day when you stand on a hilltop and look out at the land stretching away from you. Things that happen beyond your horizon are invisible to you. You cannot see them. They might as well not exist from your point of view. The event horizon of a black hole works the same way, but instead of hiding distant landscapes, it hides entire regions of spacetime. Events that happen beyond the event horizon of a black hole are hidden not just from your eyes, but from the entire observable universe. No signal, no light, no information of any kind can travel from inside that boundary to outside it. What happens inside stays inside, permanently, completely, and without exception. This is one of the things that makes the event horizon so philosophically strange and so quietly unsettling to think about, if you let your mind drift toward it. It is not a wall. It is a one-way door written into the structure of space-time itself, and the universe does not need to lock it, or guard it, or enforce it with any mechanism. The laws of physics do the work automatically, the way a river always flows downhill without needing to be told. Now, here is something that will quietly rearrange the furniture in your mind if you let it settle in slowly. The event horizon is different depending on where you are standing, or rather, where you are floating. Imagine two observers. One of them, let us call her the distant observer, is floating far away from the black hole, watching through an incredibly powerful telescope. The other, let us call him the falling observer, has crossed into the black hole's gravitational field and is falling inward, helplessly, toward the event horizon. For the distant observer, watching through her telescope, something extraordinary appears to happen. As the falling observer gets closer and closer to the event horizon, he appears to slow down. Not slightly, dramatically. His clock, as seen from far away, appears to tick more and more slowly. His movements become sluggish. His light becomes stretched and dimmed, shifting toward the red end of the spectrum in what physicists call gravitational redshift. And eventually, at the very edge of the event horizon, he appears to freeze completely. He never appears to cross the horizon. He just hangs there, getting dimmer and redder, like an image fading from a photograph, approaching but never quite arriving at the edge. That is what time dilation looks like from the outside. Gravity slows time. The stronger the gravity, the slower the clock. And at the event horizon, time, as measured from a safe distance, appears to stop altogether. But for the falling observer himself, the experience is completely different. He does not feel time slow down. He does not experience any dramatic moment of crossing. In fact, if the black hole is large enough, and some black holes are unimaginably large, he might cross the event horizon without noticing anything unusual at all. The space around him, locally, looks and feels perfectly normal. His own clock ticks at its usual rate. He can think, breathe, observe, and yet, without knowing it, he has crossed the most absolute boundary in the known universe. He is inside, and there is no way back. This is one of the deepest and strangest results of general relativity. Two observers watching the same event experience it in completely incompatible ways. One sees the fall frozen at the edge forever. The other experiences the fall continuing inward, past the edge, into the dark. Both are correct. Both descriptions are valid within their own frames of reference. The universe does not resolve the contradiction. It simply holds both truths at once, the way the night sky holds both the stillness of the stars and the vast distances between them at the same time, without apology. Let that thought rest in your mind for a moment. Let it float there, unhurried. There is no need to resolve it tonight. Some things in the universe are not meant to be resolved. They are meant to be held gently, turned over slowly, the way you might turn a smooth stone in your hand without trying to understand everything about how it formed. The understanding comes later, slowly, in the quiet between sleeping and waking. And we are just beginning. The size of an event horizon is something that scales simply and cleanly with the mass of the black hole. There is a formula, elegant in its simplicity, called the Schwarzschild radius, named after Karl Schwarzschild, a German physicist who, remarkably, derived the solution to Einstein's equations in 1916 while serving on the Russian front during the First World War. He sent his calculations to Einstein in a letter, written from the trenches, and died of illness a few months later, never knowing the full weight of what he had found. The Schwarzschild radius tells you how small you would have to compress any mass to turn it into a black hole. For the entire Earth, this whole spinning planet, with all its oceans and mountains and cities and history, that radius is about the size of a marble. A marble. If you could squeeze the entire Earth into a sphere roughly the size of a child's toy, the gravity at its surface would be enough to trap light, and the Earth would become a black hole. The Moon would continue to orbit it, utterly unchanged in its path because the total mass would be the same. Only the density would have changed. Only the impossible, unimaginable density. For the Sun, the Schwarzschild radius is about 3 kilometers. 3 kilometers, the entire mass of the Sun, 1,000,000 Earths burning at 10,000 degrees at its surface, carrying the weight of every planet that orbits it, compressed into a sphere you could walk across in about 40 minutes. And then there are the giants. At the center of our own galaxy, the Milky Way, sits a black hole called Sagittarius A star. Its mass is approximately 4 million times the mass of our Sun. Its event horizon is roughly the diameter of the orbit, heat of Mercury around our Sun. An event horizon so large that if you replaced our Sun with it, it would swallow Mercury whole and reach halfway to Venus. And Sagittarius A star is not even particularly large by the standards of the universe. There exist black holes, supermassive black holes, with masses billions of times greater than the Sun. The largest known, a monster called TON 618, has a mass estimated at 66 billion solar masses. Its event horizon is larger than our entire solar system. The distance from the Sun to the outermost reaches of our solar neighborhood, a journey that would take a spacecraft thousands of years, would fit inside that event horizon with room to spare. These numbers are not meant to frighten you. They are just numbers. Large numbers. Numbers so large they stop feeling like numbers and start feeling like something else. Like poetry, almost. Like the universe describing itself in a language that human minds can only partially translate. And as those numbers drift through your mind tonight, as you lie in the quiet and let your breathing slow, remember that every one of those black holes is doing exactly what it has always done. Sitting still, patient, waiting with the absolute boundless patience of something that does not experience time the way you do. Unchanged, unchanging. There is something strangely comforting in that, if you let it be. We are going to keep going. There is so much more to explore. What happens if you fall in? What physicists mean when they talk about the information paradox. What Stephen Hawking discovered that shocked the entire field of physics, and why some scientists believe that black holes might not be the end of the story, but something closer to the beginning of another one. But all of that can wait a few moments. Let the images you have built so far settle in. The collapsing star, the invisible boundary, the frozen clock seen from afar, the traveler who crosses without knowing. Let them drift slowly, the way clouds move on a windless night, not going anywhere in particular, just existing, quietly in the dark above you. And the dark above you right now, the ceiling, the sky beyond it, the space beyond that, is full of them, scattered through the universe like seeds, like punctuation marks in a story too long for any one mind to read. Thousands of them in our galaxy alone, millions across the observable universe, each one a place where the ordinary rules quietly fold inward and something stranger takes over. Think about what it means to have millions of these objects scattered through the cosmos, and yet your night, your room, your breath, completely undisturbed. The universe contains its extremes with a kind of effortless grace. The most violent processes imaginable sit alongside the most delicate. A flower growing through a crack in concrete, a black hole drifting through the quiet between stars, pulling nothing, disturbing nothing, simply existing at the edge of everything we understand. That is the universe. That is what it does. Now let us go a little deeper. Let us talk about what it might actually be like to fall toward one. Not into one. Not yet. Just toward one. Because the approach itself is one of the strangest journeys that physics allows us to describe. Imagine you are somewhere very far from a black hole. Far enough that its gravity is no stronger than the background hum of any other massive object in space. A distant tug, barely felt, like the gravity of a mountain you are standing 100 miles from. At this distance, everything is normal. Space looks like space. Stars are visible in every direction. Your clock ticks at its usual rate. You could be anywhere. Now imagine you begin to drift closer. At first, nothing seems to change. Space is still space. The stars are still there. But if you had instruments precise enough to measure it, you would notice that your clock is ticking very slightly slower than it was before. Not noticeably, not dramatically, just a tiny fraction of a second per day, an almost imperceptible lag. The gravity of the black hole is stretching the fabric of time around you, the way a weight placed on a rubber sheet creates a depression that spreads outward in all directions, growing steeper the closer you get to the center. This is the thing about gravity and time that is so hard to feel intuitively, because in our everyday lives the effect is so small it might as well not exist. But it is real. It has been measured. Clocks on the International Space Station, orbiting Earth at high speed and at a slightly different gravitational potential than we experience on the surface, tick at a measurably different rate than clocks on the ground. The engineers who designed the GPS satellites in orbit around our planet had to account for this time difference in their calculations. If they had not, your phone's navigation would drift off by miles every single day. Einstein's time. Dilation is not abstract. It is baked into the technology in your pocket. Near a black hole, though, this effect is not a matter of nanoseconds per day. It is a matter of hours, then days, then years, then centuries, depending on how close you are. There is a concept called the photon sphere, which exists just outside the event horizon of a black hole. It is the distance at which gravity is so strong that light itself travels in circles. Literally, a beam of light, shot in exactly the right direction at exactly the right distance from the black hole, will bend around it in a perfect orbit and come back to where it started. If you were somehow floating at the photon sphere, which is not possible for any object with mass since the orbit is unstable, you could, in theory, look forward and see the back of your own head. Light from behind you would curve around the black hole and arrive at your eyes from the front. Let that image settle for a moment. Your own face, visible in front. Of you. Because light has traveled all the way around a black hole and returned to your eyes, the universe bending its own rules in a loop. And then, closer still, there is the innermost stable circular orbit. This is the last distance at which an object can orbit a black hole without being pulled inevitably inward. Inside this boundary, there are no stable orbits. Anything that crosses it, any piece of matter, any molecule of gas, any fragment of a destroyed star, is committed. It will spiral inward. It has no choice. The mathematics of its trajectory no longer contain a solution that curves back outward, only inward. And then, the event horizon. We talked about the event horizon before, about that invisible boundary, that threshold drawn in spacetime. Now, let us think about it a little differently. Let us think about what it means for the concept of escape. Escape velocity is something you might remember from physics class, or perhaps from watching rockets launch. To leave the surface of Earth, a rocket needs to reach a certain minimum speed, about 11 kilometers per second, or it will eventually be pulled back down. The higher the gravity at a surface, the higher the escape velocity. The Moon has lower gravity than Earth, so its escape velocity is lower. A massive planet like Jupiter has higher gravity, so its escape velocity is much higher. At the event horizon of a black hole, the escape velocity is exactly the speed of light. Not almost the speed of light. Exactly the speed of light. And since nothing in the universe, no object, no signal, no information, can travel faster than the speed of light, this means nothing can escape. The event horizon is not a wall that stops things. It is the precise point at which the required escape speed exceeds the universal speed limit. It is a boundary defined entirely by mathematics, by the relationship between mass, distance, and the maximum speed the universe allows, and it holds perfectly and absolutely, without exception. Consider for a moment what that phrase means. The speed limit of the universe. We live in a world full of speed limits that are just conventions. The speed limit on a road can be changed by a committee, but the speed of light is not a convention. It is a feature of space-time itself, woven into the structure of reality at the deepest level. Nothing that carries information can exceed it, not because something stops it, not because there is friction or a barrier, but because space-time simply does not contain a path that would allow it. The math runs out, the solutions disappear, and the event horizon is the place where that fundamental cosmic speed limit meets the concentrated gravity of a collapsed star. Now, let us talk about what happens to the falling observer we imagined earlier, the one who crossed the event horizon without noticing. Suppose the black hole is very large, large enough that the tidal forces at the event horizon, the difference in gravitational pull between your head and your feet, are gentle enough to be survivable. This is true for the supermassive black holes at the centers of galaxies. For a black hole with the mass of millions of suns, the event horizon is so far from the singularity that the curvature of spacetime there is relatively mild, at least locally. You could cross it, in principle, without being immediately torn apart. So there you are, falling inward, crossing the boundary without a sound, without a flash of light, without any physical sensation that marks the moment. Just space and stars and the quiet. And then, inside, what do you see? This is one of the most extraordinary and counterintuitive results in all of general relativity. You might expect darkness. You might expect to see nothing, since no light from outside can follow you in. But that is not quite right. Light can still fall in. It just cannot get out. So you can still see the universe outside in a sense, but it looks different. Profoundly different. Looking outward toward where you came from, you would see the entire history of the external universe compressed into a single bright point above you. Light that was emitted at all different times from all different directions would be bent and focused by the extreme space-time curvature into a narrowing circle of brightness, like looking up through a hole in the ground that is slowly closing above you as you sink. You would see the universe speeding up, not slowing down, as your own time falls behind the time of the outside world. In principle, you could watch the entire future of the universe play out in the light streaming down above you, though the practicalities of surviving long enough to observe it are, to put it mildly, challenging. And looking inward, looking toward the singularity, you would see something that no equation fully describes, because the singularity is not just a point of infinite density. It is, in the language of general relativity, a moment in time, a future moment, a moment that, once you have crossed the event horizon, is as inevitable as tomorrow. You cannot avoid the singularity for the same reason you cannot avoid next Tuesday. It is not a place you are traveling toward. It is a time you are traveling toward. And every path forward in your future leads there. This is perhaps the most mind-bending thing about the interior of a black hole. Space and time swap roles. What was time? The relentless forward march toward the future. Becomes space. And what was space? The freedom to move in different directions becomes constrained. There is only one temporal direction now, and it points inward, toward the singularity, toward the end. Have you ever wondered what it would mean for time to have a direction you could not choose? We feel, always, that we are moving forward in time, that the future is ahead and the past is behind, and while we cannot go back, at least we can slow down, stop, rest, sleep. But inside a black hole, even that freedom disappears. Time flows only one way, and that way has a terminus. It is a strange thing to sit with, and yet, and here is one of those moments where physics reaches into philosophy, physicists are not entirely sure the singularity is real in the way we usually mean real. The singularity might be a sign that our equations are incomplete. When a formula produces an infinite result, physicists often treat that infinity not as a description of reality, but as a symptom of a theory breaking down, a sign that something is missing, that we need a better theory, one that works at the scale of the very small, the quantum scale, where general relativity and quantum mechanics, the two great pillars of modern physics, have never managed to agree with each other. The singularity, in other words, might be where our current understanding simply runs out of words. And running out of words, in the right circumstances, can be the beginning of something new. Let us step back for a moment. Let us move away from the interior and look at black holes from the outside again, from the comfortable distance where the equations stay well behaved and the concepts, while still strange, are at least describable. From the outside, a black hole is defined almost entirely by three numbers. Just three. Its mass, how much stuff collapsed to form it. Its electric charge, which for most astrophysical black holes is effectively zero, since matter in space tends to be electrically neutral, and its spin, how fast it rotates. That is all. Three numbers. This is known in physics as the no-hair theorem, a phrase coined with a kind of wry humor, the idea being that a black hole has no extra features, no texture, no individuality beyond those three quantities. All the complex history of whatever fell in, the stars, the gas, the planets, the light, is gone, absorbed. The black hole does not remember. It holds the total mass, the total charge, and the total angular momentum. Everything else is erased. Think about what that means. A black hole might have formed from a star 10 times as massive as our Sun, or from 1,000,000 smaller stars, or from an incomprehensible amount of cold gas compressed over billions of years. It might have swallowed planets. It might have swallowed other black holes, and from the outside you cannot tell. You cannot reconstruct the history. The information, in the everyday sense of the word, is simply gone. Or is it? This is where we arrive at one of the most famous unsolved problems in all of physics, the black hole information paradox. In the early 1970s, Stephen Hawking, perhaps the most famous physicist of the latter half of the 20th century, was thinking about black holes through the lens of quantum mechanics. Quantum mechanics is the theory that governs the behavior of the very small, atoms, electrons, photons of light. And one of its most fundamental principles is that information is conserved, not matter, not energy in any particular form, but information, the underlying description of any physical system, can never truly be destroyed. It can be scrambled beyond any practical hope of recovery, like a document fed through a shredder, but in principle the information is still there. It has not ceased to exist. The shredded pieces contain, in total, the same information as the original document, just in an incredibly disordered form. Hawking began to wonder what quantum mechanics had to say about the event horizon, and what he found in 1974 was something that shook the physics world to its foundations. He found that black holes are not entirely black. They glow, not with ordinary light, not with a brightness you could see or measure with any telescope pointed at a real black hole in the sky. But in the quantum mechanical sense, black holes emit radiation, a slow, cold, steady trickle of energy leaking out from just outside the event horizon, produced by an extraordinarily subtle quantum effect. This radiation, now called Hawking radiation, naturally carries energy away from the black hole, and as it does, over an incomprehensibly long time, the black hole slowly loses mass. It evaporates. The mechanism is beautiful in its strangeness. In quantum mechanics, empty space is not truly empty. It seethes with what physicists call virtual particles, pairs of particles and antiparticles that pop into existence and annihilate each other so quickly that they cannot be directly detected in ordinary circumstances. They are like bubbles that form and burst on the surface of water, gone almost before they appear. But near the event horizon, something unusual can happen. One particle of the pair falls inside the horizon, and the other escapes. The escaping particle carries away real energy, energy that, by the accounting of general relativity, must come from the black hole's mass. Over time, the black hole shrinks. Now, here is where the paradox bites. Hawking radiation, as originally calculated, is perfectly thermal. It carries no information. It is pure noise, like the static of a radio tuned to a dead channel, which means that as a black hole evaporates, as everything that ever fell into it is slowly converted into this featureless thermal radiation, all the information about those infalling objects appears to be permanently, irreversibly destroyed. But quantum mechanics says information cannot be destroyed, and general relativity says information cannot escape from inside a black hole. These two great theories of physics, each enormously successful in its own domain, are making directly contradictory statements about the same physical situation. One of them must be wrong, or incomplete, or we are missing something that lies beyond both of them. The physics community has been wrestling with this for 50 years. Various solutions have been proposed. That information is somehow encoded in the Hawking radiation after all, in correlations so subtle that Hawking's original calculation missed them, that there is a kind of quantum bridge, a wormhole, that preserves information, that the singularity is not real, and information escapes when the black hole's geometry changes at the Planck scale, the smallest meaningful scale of distance in quantum gravity, that something called a firewall exists at the event horizon, where the falling observer is actually incinerated rather than passing through unscathed. None of these solutions is universally accepted. The problem is open, and in that openness, in that beautiful, stubborn refusal of the universe to be fully understood, there is something that feels almost alive. The universe keeps its secrets carefully. Slowly now, let the information paradox drift. You do not need to solve it tonight. Some of the most brilliant minds in the history of physics have not solved it yet, and they have had decades. You have a pillow and a quiet room and the luxury of simply letting it float. In the background of your mind, a gentle, unsolved riddle humming at the edge of sleep. Think instead about something simpler, something observable. In 2019, a collaboration of over 200 scientists called the Event Horizon Telescope announced that they had done something that most physicists thought would be impossible. They had taken a photograph of an event horizon, not a simulation, not an artist's impression, an actual image constructed from radio telescope data gathered simultaneously from observatories on multiple continents, the whole Earth functioning as a single enormous telescope, pointing at the center of a galaxy 55 million light-years away. The galaxy is called Messier 87. The black hole at its center has a mass of 6.5 billion suns, and the image, blurry, orange-tinged, almost dreamlike in its quality, shows exactly what Einstein's equations predicted over a century ago. A bright ring of superheated matter, glowing as it spirals inward, surrounding a dark central shadow. The shadow of the event horizon, the first direct visual confirmation of one of the strangest predictions ever written on a piece of paper. When the lead scientist of the project, Katie Booman, first saw the image appear on her computer screen, the photograph shows her covering her face with her hands, not in distress, in something harder to name. The expression of a person seeing for the first time confirmation that a thing they have dedicated years of their life to is real, not theoretical, real, there in the light, 55 million light-years away, and we could see the shadow it casts. There is something in that image that goes beyond science, that circle of light around the darkness, that glowing ring at the edge of the unknown, feels like something humans have always been reaching for. The boundary between the known and the unknowable, the circle drawn around the mystery, not to contain it, but to honor it, to say, here is where our knowledge ends, and here is where something else begins, and it is beautiful. It is, in its strange, blurry, astronomical way, beautiful. Let that image rest in your mind for a moment. The orange ring, the dark center, the 55 million years that light traveled to reach our instruments, the equations that predicted it before we had the instruments to see it, the 200 scientists from dozens of countries who work together across time zones and languages and disciplines to make the seeing possible. All of that converging on a single blurry circle on a computer screen, and a woman covering her face with her hands. That is science. That is what it looks like when human curiosity runs all the way to the edge of what is knowable and peers over. And tonight, from your bed, you are peering over that same edge, not with a telescope, with something older and stranger than any telescope, with the capacity to imagine, to take words and numbers and equations and transform them into something felt, into a sense of vast distances, of impossible densities, of time stretched like taffy near the edge of a gravitational well. The universe gave you that. It gave you a brain capable of modeling things it will never experience directly, things so extreme that no human body could survive them, and still finding them beautiful. That is not nothing. That is extraordinary. We will go deeper still in the final part of tonight's journey. There are things left to explore. The different kinds of black holes, the spinning ones that drag spacetime itself around with them like water spiraling around a drain, the strange theoretical objects that might exist at scales smaller than atoms, and the quiet philosophical question that sits beneath all of this like bedrock, the question of what black holes tell us about the nature of reality itself, about what space and time actually are, underneath the familiar surface of ordinary experience. All of that waits for you, but let it wait gently. Let it wait the way things wait in the dark. Not urgently, not pressing, just present, resting at the edge of your awareness, the way a dream waits at the edge of sleep, not demanding entry, just available, soft and patient, ready to unfold when you are ready to receive it. And you are drifting now. You can feel it, perhaps. The slow loosening of the day's tensions, the weight of the body settling more completely into whatever is beneath you, the breath becoming a little slower, a little more automatic, a little less something you are doing, and a little more something that is simply happening, the way tides happen, the way seasons happen, the way light from a star 55 million light-years away travels through the dark without effort or intention, simply following the shape of the universe it was born into. That is where we are now, following the shape. Let us talk about spinning black holes, because most black holes in the universe do not sit perfectly still. They spin. And a spinning black hole is something stranger, and in its way more beautiful, than the simple non-rotating version we have been imagining up to now. When a massive star collapses, it almost always carries some rotation with it, a slow turning inherited from the original cloud of gas and dust that formed it. The same way a figure skater spinning with arms outstretched will spin faster when she pulls her arms inward. As the star collapses, that rotation speeds up, dramatically, the way the skater's does. By the time the collapse is complete and the black hole has formed, the spin can be enormous. Some black holes are estimated to rotate at a significant fraction of the maximum possible speed, which is itself defined by the speed of light. A black hole spinning at its absolute limit would have its equator moving at the speed of light. Any faster is not allowed. The universe will not permit it. A spinning black hole is described by a different set of equations than a non-rotating one. A solution called the Kerr metric derived in 1963 by a New Zealand mathematician named Roy Kerr, working at the University of Texas. It took nearly 50 years after Einstein's original theory for anyone to find the rotating solution, and when Kerr published it, the reaction from physicists was one of almost disbelieving admiration. The equations were extraordinarily complex. The implications were even more so, because a spinning black hole does something that a non-rotating black hole does not. It drags spacetime around with it. Imagine you are stirring a very thick liquid, something like honey, slow and viscous. As you move the spoon in circles, the honey near the spoon is dragged along, rotating with it. Space near a spinning black hole behaves something like that honey. The rotation of the black hole twists and drags the spacetime around it, so that even an object trying to stay completely still, trying to remain fixed in space, not orbiting, not falling, just hovering, will find itself being slowly pulled around in the direction of the black hole's spin. There is no way to resist it. It is not a force you can push back against. It is the very fabric of space itself rotating around you, and you are carried with it whether you want to be or not. This effect is called frame dragging, or the lens-thirring effect, and it has been measured around the Earth itself. Our own planet's rotation produces a tiny, tiny version of the same phenomenon, so small it required the most sensitive gyroscopes ever built, flown aboard a satellite called Gravity Probe B to detect. But near a rapidly spinning black hole, frame dragging is not tiny at all. It is overwhelming. It defines the geometry of the space around the black hole for a considerable distance outward. For a spinning black hole, there is a region outside the event horizon called the ergosphere. The name comes from the Greek word for work, ergon, because the ergosphere is a region from which energy can actually be extracted from the black hole. This was proposed by the physicist Roger Penrose in 1969, in what is now called the Penrose process. The idea is that inside the ergosphere, spacetime is rotating so fast that it is impossible for anything to remain stationary. Everything is carried around with the spin of the black hole, like leaves on the surface of a whirlpool. But unlike the region inside the event horizon, the ergosphere is still in the external universe. Things can enter and leave it. And in principle, a cleverly arranged object entering the ergosphere, splitting into two pieces, and allowing one piece to fall inward along just the right trajectory, can cause the other piece to fly outward with more energy than the original object had. The extra energy comes from the rotation of the black hole itself, which slows very slightly as a result. In other words, a spinning black hole can be a source of energy, not just in theory. Astrophysicists believe that the enormous jets of plasma that shoot out from the poles of some supermassive black holes, extending for thousands of light years into space, are powered in part by exactly this mechanism. The rotational energy of the black hole slowly being converted into the kinetic energy of matter flung outward at nearly the speed of light. A black hole that is, in a sense, doing work, giving something back to the universe, even as it consumes. Think about that for a moment. We have spent time tonight thinking about black holes as ultimate consumers, as one-way doors through which matter and energy disappear forever. And yet, here is a spinning black hole, giving energy back, driving jets of plasma that seed the intergalactic medium with matter that may play a role in shaping the formation of galaxies that are visible from billions of light years away. A black hole that, through its spin, becomes a kind of engine, not a destroyer, a transformer. The universe rarely deals in pure opposites. Now let us drift toward something smaller, much smaller, because not all black holes are the giants we have been imagining. The stellar remnants 10 times the mass of the Sun, the supermassive monsters at galactic centers. Physicists have long theorized about the possible existence of something called primordial black holes that did not form from the collapse of stars, but from the extreme densities of the very early universe, in the first fractions of a second after the Big Bang. In those first moments, the universe was unimaginably hot and dense, so dense that random fluctuations in the distribution of matter, tiny regions slightly denser than their surroundings, the way a handful of sand is not perfectly uniform, could have been sufficient to cause local collapse, to pinch off small regions of spacetime into black holes before any stars had formed, before any galaxies existed, before the universe had cooled enough to allow atoms to form. These primordial black holes, if they exist, could have masses anywhere across an enormous range. Some might be as massive as thousands of suns. Others might be tiny, as small as asteroids, or smaller. There is even speculation, purely theoretical, about black holes with the mass of a mountain compressed into a space smaller than an atomic nucleus. At those scales, Hawking radiation would be so intense that such a black hole would evaporate almost instantly on cosmic timescales, though a black hole with the mass of a mountain would still take longer than the current age of the universe to fully evaporate, because even Hawking radiation is extraordinarily slow for any black hole massive enough to have formed in the early universe. And here is something that connects the very large to the very small in a way that feels almost designed, though of course it is not designed. It is just the universe being consistent with its own rules. The temperature of Hawking radiation is inversely proportional to the mass of the black hole. A more massive black hole radiates more coldly. A less massive one radiates more warmly. The supermassive black hole at the center of the Milky Way, Sagittarius A star, with its 4 million solar masses, has a Hawking temperature so close to absolute zero that it is completely unmeasurable against the background radiation of the universe. It will take something like 10 to the power of 87 years to evaporate. A number so large that writing it out would take more digits than there are atoms in the observable universe. And yet, the process is happening right now, one slow quantum at a time. Patience is not something the universe runs short of. Consider for a moment what it means that the universe contains objects measured in units of billions of solar masses, engaged in a process that will take 10 to the 87th years to complete. The universe is approximately 14 billion years old. It has existed for 1 times 10 to the 10th years, roughly. The evaporation of a large black hole will take a number with 87 zeros. We are at the very beginning. The universe is, by any meaningful measure, extraordinarily young. Most of its duration lies ahead of it, in the dark, in the slow cooling and dimming and evaporation of things we have barely begun to understand. You are falling asleep in the early universe. There is something quietly remarkable about that. Every human being who has ever lived has existed in the first small fraction of the universe's total duration. The pyramids of Egypt, ancient as they feel, are a recent development by cosmic standards. The first stars, burning bright and blue and enormous in the early universe, would consider our sun a relative newcomer. And the black holes forming today, the stars collapsing right now, at this moment, somewhere in the 1,000 billion galaxies of the observable universe, will outlast everything we can currently see. They will be there when the last star goes cold. They will be there when the galaxies have dispersed. They will drift through a dark, empty, cooling universe for a duration that makes the current age of everything seem like a blink. And slowly, one Hawking photon at a time, they too will fade. What happens then? What happens at the very end of a black hole's life? Physicists call it the black hole evaporation endpoint, and it is one of the genuinely open questions of modern physics. As a black hole loses mass through Hawking radiation, it gets hotter and radiates faster. The final stages of evaporation are thought to be extremely rapid. A burst of radiation, a flash of energy, a moment of tremendous release, and then nothing. The singularity, if it was ever real, is gone. The event horizon, without mass to sustain it, dissolves. The black hole simply ceases to exist. What remains? Perhaps a faint smear of radiation, spreading outward through a universe so old and cold that there is almost nothing left to witness it. Perhaps something stranger, some relic, some Planck-scale remnant, an object so small and so dense that our current theories cannot describe it. Perhaps nothing at all, in any meaningful sense. The information paradox looms over this question too, because if the black hole evaporates completely, everything that ever fell in must somehow be encoded in the outgoing radiation, or be genuinely, permanently lost. And that question, the question of whether information can truly be destroyed, is not just a technical puzzle about black holes. It is a question about the deepest structure of reality, about whether the universe is fundamentally reversible, whether every state can in principle be traced back to the state before it, whether the past is truly encoded in the present in some complete and irrecoverable way, whether the universe is, at its most fundamental level, a place where nothing is truly forgotten. Have you ever wondered if memory works the same way? If everything that has ever happened, every thought, every conversation, every moment of light falling through a window, leaves some trace in the structure of the world, however faint and scrambled and impossible to recover, whether the universe itself remembers in its own cold, quantum, mathematical way. Physics does not answer that question, but it asks it in its own language. And the language of physics, when you follow it far enough, starts to sound less like equations and more like the oldest questions human beings have always asked, lying in the dark, looking up at the stars. What is real? What persists? What is time? What are we in all of this vastness? There is no need to answer those questions tonight. There is no need to answer them at all in any hurry. They are the questions that keep being asked, generation after generation, by minds that look up and feel the pull of the unknown. The same pull that draws matter toward a black hole. Not destructive, not cruel, just the simple, unavoidable tendency of the universe to draw things toward what is deepest. Let the questions drift. Let them be like light at the edge of an event horizon, present, luminous, endlessly approaching but never quite crossing over into resolution. That is all right. That is more than all right. The approaching is the thing. The wondering is the thing. And now we are near the end of tonight's journey. The journey that began with an image, a place where light cannot escape, where time slows to stillness, where the ordinary rules fold quietly inward, and that has carried us through collapsing stars and invisible boundaries, through time dilation and information paradoxes, through spinning black holes that drag space-time like honey around a spoon, through the extraordinary image of a glowing orange ring 55 million light-years away, through primordial black holes smaller than atoms and supermassive ones larger than solar systems, through the slow and patient evaporation of objects that will outlast everything else in the universe. All of that, from this quiet room, from this stillness. Think for a moment about the event horizon one more time, that boundary we have returned to again and again tonight, in different words, from different angles, like a stone turned slowly in the hand. It is, at its core, a boundary between the knowable and the unknowable, between the region where information can travel outward, where signals can escape, where the universe can know what is happening, and the region where it cannot. A line drawn in space-time, not by any mind or intention, but by the laws of physics themselves. And there is something in that image, the event horizon as a boundary of knowability, that resonates beyond astrophysics, because we all carry something like an event horizon within us, a threshold beyond which certain things cannot be fully communicated, fully transmitted, fully known by anyone outside. The inner life is its own kind of sealed region, radiating warmth and light from its edges, hinting at what lies within, but ultimately unreachable from outside. You cannot transmit the interior of your experience across the boundary of language any more than light can transmit information from inside a black hole. You can only glow at the edges. You can only let the warmth of what you are leak out slowly, particle by particle, into the world around you. That is not a tragedy. That is just the shape of things. The universe is full of sealed regions, full of interiors that cannot be accessed from outside. And yet those sealed regions, those black holes, those inner lives, those private experiences, are not absent from the universe. They are present in it. They curve the space around them. They exert gravity. They change everything in their vicinity simply by existing, simply by having mass, simply by being there. You do not need to be fully known to matter. Let that drift with you for a moment. The stars above you tonight, above the ceiling, above the roof, above the atmosphere, spreading out in every direction across the observable universe, are engaged in processes we have been slowly, humbly learning to understand for only a few centuries. And the black holes scattered among them, invisible in themselves, visible only through their effects, are doing what they have always done, sitting still, curving space-time, holding their interiors in perfect, permanent silence. They have been there longer than our planet. They will be there long after our sun has burned out and expanded and cooled into a white dwarf and finally gone dark. They are patient in a way nothing else in the universe can match. Patient and quiet and immovable, and in their way, magnificent. And you are here. For a brief, improbable, luminous moment, you are here. On a small rocky planet orbiting an ordinary star in the outer arm of a middling galaxy, lying in the dark, letting your mind drift through spacetime, through ideas and images, and questions that humans have been slowly assembling for centuries, piece by careful piece, into a portrait of a universe stranger and more beautiful than anyone could have imagined. The event horizon is out there, billions of them, each one a perfect circle drawn in the fabric of reality, each one a place where the ordinary story of the universe pauses, folds inward, and becomes something we cannot follow. You do not need to follow it tonight. You are on the outside, safe in the warm, accessible region of spacetime where time flows forward at its ordinary rate, where light travels freely in all directions, where the night is soft and the breath is slow, and the distance between you and the nearest black hole is so incomprehensibly vast that it might as well be a different universe entirely. Let the black holes drift in the dark between the stars where they belong. Let the questions they carry drift with them. Let the image of that orange ring, glowing against the black, rest. Somewhere in the back of your mind, like a nightlight left on in a far room. Warm, faint, and quietly extraordinary. The universe is vast. You are small within it, and that smallness, held gently without fear, is one of the most peaceful feelings available to a human mind. To be small in something beautiful, to be a brief, luminous point in a cosmos that has been here for 14 billion years and will continue for trillions more, doing its patient, extraordinary work of curving and collapsing, and burning and drifting, and, occasionally, bending light around itself in a perfect circle and glowing orange against the dark. Rest now. Let the space-time curve around you gently. Let the breath slow to its own natural rhythm. No effort required, no destination to reach. Let the event horizon exist where it exists, and let your mind exist where it exists. Here, now. Warm, still, drifting toward the quiet interior of sleep, where no signal needs to escape, where nothing needs to be communicated or understood or resolved. Just the dark, just the breath, just the vast and patient universe doing what it has always done, in every direction, at every scale, without hurry and without end. Good night.